3. My baby don't mess around. Okay. I'm not splicing that out if you know that.
No, that's good. That was thumbnail-alicious.
Yeah.
Never mind.
That was the most high yield thing on the MCAT.
The thumbnails. There you go. Hope you enjoyed the application.
All right. Welcome back to another application session, guys. If you're following along,
Who killed your cat?
it's not. She's over in the corner. I worked all day.
Oh my gosh. Alrighty. Well, I did too, but I've had more caffeine than you. Go ahead. Go ahead.
I was just gonna say that we are in the CP4. I think it was week 9 of your material, of your content, and we're gonna pull out some of the highest yield things and then show y'all how the AAMC likes to test it, as per the usual. There's not a lot of high yield material though this week.
There's a ton of mid yield, a lot of like mid yield material. So don't. Usually, and Maggie and I were talking about this beforehand. Usually, the stuff we have you review in the chapters is like if you're aiming for like 510 plus. Or let me back up. The stuff that's not in the application sessions that is in the chapters is usually for like if you're aiming for like 510 plus, maybe even like 508ish, some of that low yield stuff. But the mid yield stuff, you really do want to you do want to learn it. It's just you don't have to super conceptually love it. You know, you don't have to ensure that you know every single square inch of it and how to apply it in 56 different shades. That's what the high yield is, right? Like you have to know everything. You need to know your amino acids, everything about them, what it would look like, and what would they be protonated or deprotonated at a pH of 1, and different things like that. But the mid yield stuff is a little bit closer towards that. I'm rambling now, but
John, do you mind if I go ahead and mention a couple of the mid yield things? Like, I'm not going to go too deep into it, just mention them real quick so I don't forget.
No, I don't care what you do.
All right. So lenses is in this chapter. And it's gone over in very good detail because the MCAT reserves the right to test any of the stuff that's in that content guide. But if I was going to point out some of the things to focus on lenses, I would say, real, what is the saying, John? It's like a real image is negative and inverse or something like
positive that. Yeah, it's positive real inverted, negative virtual upright.
Yeah.
PRI NVU.
Yeah.
Pré and vu.
Pré and vu. So yeah. Know that. And then I think I've seen a few equations on lenses that were like the focal length given the
thin lens
or something. Yeah.
You gotta know the thin lens equation.
Yeah, the thin lens equation, and then like the power equation that's like the inverse of the focal length or whatever.
I've seen one question on that one that was so hard that I just told the student I was tutoring at the time, like, we're just gonna send it. Like, I don't know how to do this one.
That's what I'm saying. Like, I don't think I've ever seen any other like equations or like lens stuff on the actual MCAT, but I did see that on a practice exam or something. So I want to throw it out there.
Yeah, there's one on like AAMC 1 or 2 that's just like, nope. No, I will straight up click past it.
Yeah. I mean, if I had lenses on my MCAT, I think I'd take the L. I'd be like, I'd just get out of the MCAT and then sign up for the next time slot and hope it's a different test. But y'all
right, so what we got today?
We're gonna do great and study lenses, unlike me. But let's get into actual high yield stuff. John, you, me?
Yeah, I can talk about IR spec. So infrared spectroscopy is a lab technique, and lab techniques in general, like the OChem lab techniques, are very high yield. Anytime you see something that's like chromatography or spectroscopy, you better freaking know it because A, it's going to be on your test, and B, they're cake points. It'll be like which of these will elute last in a cation specific chromatography column. And all you literally have to know is what that is, and then you can get it. And IR spec, basically the idea is that we're going to take some IR waves and we're going to smash these different chemicals with it, and they are going to absorb. It actually deals with resonance. Their bonds are going to become in resonance with different wavelengths of the IR waves that you smash it with, but that's a little bit beyond what you're really going to have to super understand. What you need to understand is that these bonds will absorb at specific wavelengths. And again, real life is they're just resonating at those specific wavelengths, and we call it absorbance. But for practical purposes, this is an application session, not a lecture. We're looking at absorbance, and you really need to understand, or you need to understand what it is. Basically, I'm taking IR waves, I'm smashing it with it, and it's going to help me to separate functional groups based off of these absorbance patterns. That's what you need to understand. Everything else with IR spec, you just have to memorize the functional groups absorbance patterns and the wavelengths or the frequencies at which they absorb. Right, Max? Can you think of anything else?
No, the only other thing I would say is that in your content guide, it gives a whole big long table that's like 10 or 12 different functional groups. If you want to learn all of those, that's cool, and you're going to be even more prepared. But I put the three most common ones that you need to know and you need to be able to identify on a graph. I popped them up here. It's the alcohol groups, the sp3 hybridized CH bonds, and the carbonyls. And then I gave the absorbances as well. So I have it labeled here, but like this, anytime it kind of has like a broad, deep, strong and broad signal around the 3200 to the 3400 range, that's going to be indicative of an alcohol or an OH group. These spikes down here, if there wasn't an alcohol in, this butanoic acid or whatever that is, then it would look like just like spikies right here. But since it has alcohol, it kind of like covers it up a little bit. But this right here is indicative of an sp3 hybridized CH bond. And then the carbonyl is the most high yield. It gives this characteristic really deep, strong, sharp peak at 1700. So those are the most high yield. If you want to get the most bang for your buck, those are going to be the ones that you memorize and are able to, identify on a graph.
Yeah, carbonyl's gonna be on your test. 1700. Yeah. If I have a student that misses that once, I'm like, okay, that's fine. There was a time I didn't know it. If you miss that twice, my hand just starts twitching. I can't stand it. But Maggie, do you know why the alcohol's band is so broad?
Is it the polarity?
I don't know. There's actual science reason for it.
Thought you were testing me.
No. I'm not. You did good on your MCAT. You don't have to do this anymore. I don't have to test you anymore. The gosh, there's an actual science. If somebody remembers it, comment it below because it's gonna kill me inside. But yeah, you make sure you know these three. The other ones are great. Some of the amine ones are helpful, but these three, yeah, don't pause the video and make sure that you got a flashcard for these because you shouldn't leave this video without knowing these three. And I've seen alcohol go as high as 3,500 inverse centimeters. Some books will say 3,500. And so be on the lookout for that.
Yeah. One more thing, if you're not familiar with IR at all, then this graph might be confusing to you. I do want to point out that these graphs look different for every single molecule that you run an IR spec on. So the whole reason you're running an IR spec is to see, if you have an unknown compound, you run it through IR spec and you can get an idea of what kind of functional groups you have on your compound. So that's why, this molecule sitting over here, that's because this is the IR spectra for butanoic acid. So it's going to look different no matter what it is. So don't memorize this graph, memorize the common absorbances, the actual numbers, and then memorize kind of like how they look. Is it, really narrow and sharp like carbonyl, or is it kind of rounded and broad like alcohol?
And technically this and NMR, which is another popular lab technique, you could, somebody that was good could look at this and be able to tell what the molecule was. You might have had to do that in undergraduate. You do not have to do that for the MCAT. Okay, what Maggie told you is what's on the test, which is you might see a graph, but you probably won't. It'll probably be a pretty cake question that's like, hey, this molecule has a sharp absorbance band in an IR spectroscopy of 1700 inverse centimeters. What functional group is this indicative of? You're going to click carbonyl. You're going to thank God that you watched this video. You're going to go to the next one.
Let's actually see how this is tested by a real question. I'll take it because John so eloquently explained what IR spec is. So, this reaction was given in the passage. This is not a standalone, this is a passage question. So this reaction was given, but I pulled it for the question. It says mevalonate, compound 2 in reaction 3, is expected to display prominent absorption in which regions of its IR spectrum. So if I was going to simplify this question, I would say, what does an alcohol, like what absorbance is an alcohol? What absorbance is a carboxylic acid, or specifically a carbonyl? What absorbance is a CH3 or an sp3 hybridized CH bond? Because that's the only functional groups that are in this mevalonate. So I'm going through now because it gives us kind of a few options. I'm just going to mark off or say, yes, those would be present. So in an IR spectrum for this compound 2, would I see absorbance in this range? Well, that's the alcohol range. So just like John said, 3,500, sometimes it goes up to 3,500. And so, yes, I would see that because look, I have an alcohol right here and right there. And if it was protonated, then I would have one right there. But yes, I would see that. Okay. Would I see, what is that? A carbonyl? Yeah, absolutely, right? Because there's one right here. It doesn't matter that the carbonyl is part of the carboxylic acid because those show up as two different absorbances on an IR spec. Like there's a carboxylic acid one, but really I'm focusing on this 1700 to 1750, that's a carbonyl, and I do have a carbonyl in the compound, even if it's part of the larger carboxylic acid group. So yes, I would have that. Would I have this one? You'll notice that this is not one of the high yield ones. This is actually in your content guide. It says that this is like the aromatic double bonded C to C, carbon to carbon bond. So that's not a very high yield one, but it did show up in this question. So that's why I'm saying you'll be even more prepared if you know the entire chart. So do I have that in this compound 2 over here? No, I do not. There's no double bonded carbons. So B is the right answer.
So I want to add something to this. Just your psyche when you're taking the MCAT, and it happens in med school as well. You as a student watched this video and you saw, Maggie freaking 100th percentile, and I'm the D-bag that coached her to it, and we basically said learn 3 of them, and you see 2 of them. You see the hydroxyl group that is in your compound, and you see the carbonyl group that is in your compound, and you get to the 3rd one and you're like, I don't know what the F that is. Like, what the bump is that? And you're looking at your answer choices and you're like, I know 1 and 2 are right, but look at D. Like, I don't know what number 3 is. When that happens, and that will happen with something, go with what you know, not what you don't know.
Mm-hmm.
Okay, because in undergraduate, you got rewarded pretty heftily for saying, 3 looks like something that I don't know, and there's some stuff I don't remember from lecture, so I'm gonna go with all of them. Usually that was the right way to do it in undergraduate. That is not how it works on the MCAT, and that is not how it works in medical school, because like, you have to be confident with saying, I know what I know, and there are other variables around it that I don't know, but I know what I know, and that's what I'm going to stick with. So that's a really, really powerful, like, psyche. You've got to approach the MCAT like that. Otherwise, you're just going to get overwhelmed, and you're going to crap your pants in psych soc.
I literally was going over, I think it was the strategy session that I just did where I recorded it because it was Labor Day. And I literally gave this exact same talk, John. I was like, I don't know what depth of processing means, but I know that spreading activation is a good answer. So I'm not going to get all tripped up on depth of processing. So yeah, that's definitely a good tip. I've had a student that told me that they picked an answer just because they didn't know what it was. And I was like, a part of me just died.
Stupid. I'm just kidding. I'm just kidding.
Not stupid. Just not a seasoned test taker at that point.
Yeah, you just don't know how to cheat the test, cheat your way through med school.
They'll get there. We're gonna cheat the whole way. Okay. All right, I'll cover types of radioactive decay. So I know that my very first passage on my actual MCAT was on radioactive decay, and I thought I had it in the bag, and it was like the hardest passage on my entire MCAT. So I'm going to show you what actually is important to know about radioactive decay. So I would say the most high yield things are just knowing the names of the decay and kind of how the types of decay change the mass number and the atomic number, and a little bit about like what the actual process of the decay is. So beta decay actually encompasses 3 different types of radioactive decay. There's beta minus decay, where theoretically a neutron becomes a proton, right? So we have a neutral charge, it's 0, and it becomes a positive charge. So how does it do that? It's kind of losing a negative charge. These are a little bit abstract ways of thinking about this, because we don't really think about elements or atoms just losing charges left and right. But in this case, we think about a neutron becoming a proton by losing a negative charge, an electron. So think about it, guys. If I'm gaining a proton because a neutron's becoming a proton, my atomic number, which is my amount of protons, is going to increase by 1. But the mass number, because I lost a negative charge, but remember that the negative charges are so small that they really don't contribute to the mass at all. So the mass number is going to stay the same. Okay. Another type of beta decay is positron emission. And so that's when a proton becomes a neutron by losing a positive charge. So the atomic number is going to go down, and the mass number is still going to stay the same. Because a proton and a neutron weigh about the same. And you're not losing a proton. I want to make that clear. You're not losing a proton, you're losing a positron, which is, I don't even really know how to explain what a positron is. I think it goes a little bit too deep into like
it's antimatter is what it is.
Yeah, it's an electrochemistry, electrophysics type thing, but you're not losing a proton. So your atomic number is going to decrease by 1, but your mass number is still going to stay the same because you're just losing a positron. And then electron capture is exactly what it sounds like. We gain a negative charge, and so a proton becomes a neutron. Atomic number is going to decrease and mass number stays the same. Other types of decay besides beta decay are going to be alpha decay. So that's the emission of an alpha particle. Okay, an alpha particle, think of that as a helium nucleus. And so what does that mean? Helium is the second element. So it has 2 protons and 2 neutrons in its nucleus. So we're losing a helium nucleus essentially. So we're losing 2 protons and 2 neutrons. How is that going to affect the atomic number and the mass number? Losing 2 protons, so the atomic number is going to decrease by 2, but I'm losing 2 protons and 2 neutrons, so the mass number is going to decrease by 4. Another type of decay is gamma decay, and that's what we think of as like the dangerous decay that Chernobyl is like giving off right now. That's the emission of gamma photons, which have no mass or charge. They're just really high energy particles. Think of gamma rays. They're really high energy that cause cancer. So highly dangerous, can only be stopped by lead, and there's no change in mass or atomic number, because remember, it's just energy. All right, that was kind of long-winded, John. Do you have anything else to say?
Yes, you did a good job. The positron emissions, you will sometimes see it called beta plus decay, which makes sense. Beta minus, you're losing an electron. Beta plus, you're losing a positron, which is literally just a positively charged electron. Okay, so that's the only caveat to this. But I've had a lot of students that say, well, I don't know how in depth I need to learn this stuff. And positron emission is a really, really good example to help you understand how deep you need to go for this. So you need to know everything that Maggie just told you. But you do not need to know what a positron is, because you're about to get into some deep crap, because a positron is the antimatter derivative of an electron, and you're going to get into this idea of what the heck is antimatter. Okay, so you don't have to, you kind of take that step and you're like, that water's cold. Don't jump in there. Don't jump in there. Okay, take a step back.
Yeah, no one's forcing you.
Yeah, nobody's forcing you. We generally, in our guide and in any test prep book, you're going to get told enough to get the questions correct. What you, as far as researching around that, is just for the concept to stick in your head. So positron emission, the idea of looking at it as a positively charged electron, that's going to stick in your head. That makes sense. You don't have to understand that it's antimatter or what antimatter is.
Mm-hmm.
So that's kind of when you know you've gone too far.
Yeah. All right. So let's see how this is actually tested. John, do you want to?
Yeah, we had a radiologist come and talk to us, give a lecture to us about PET scans. So I'll take it. It says positron emission spectroscopy. PET imaging involves injecting a patient with a positron, anti-electron, I told you, emitting isotope. The emissions of positrons occurs during, okay, this is very MCAT. They give you this thing at the beginning. It's kind of medicine-y, but it's also just pretty much straight chemistry and physics. And then they actually ask you the question at the very end. The emission of positrons occurs during what? So I'm going to rephrase this question as, which of these shoots out a positron? Okay, A says alpha decay. No, that's you spitting out a helium nucleus. B says alpha absorption. I'm gonna assume that you taking in a helium nucleus, because it sounds like the opposite of alpha decay. C says gamma absorption. I'm gonna assume that you taking in some type of wave, powerful energetic wave, because gamma decay is emission of a powerful energetic wave. And then D says beta decay. And remember we talked about how beta decay could encompass those 3 different types of decay that Maggie went through. And one of those is positron emission, or beta plus decay. So the emission of positrons occurs during D, beta decay. Final answer.
Boom, correct answer. Notice how he didn't know what either one of these are. I don't either. I don't even know if they exist. Don't worry about them. You know the answer. Why would you pay attention to anything else?
I have a physics degree and I don't know if they're real.
I have a psychology degree. I don't know if anything's real.
For real. You just got less convinced that things were real as you went on.
Learned a little bit of witchcraft along the way.
There you go.
All right, periodic table trends. I would say I don't know why I'm like stalling on teaching this.
So I don't know what this is.
I've seen it in years.
So
Um,
periodic table trends, in all honesty, the way that I did this is I just kind of learned what everything was, and then I memorized electronegativity and just based everything off of electronegativity. I know some people base it off of atomic radii or radius, but electronegativity to me is the one that like conceptually makes the most sense.
yeah.
Even though if you go deep and you dig into it, then atomic radii initially leads to electronegativity. You're getting into things like strong nuclear force, and boom, that water's too cold. Jump back. So you can memorize all the trends if you want. Maybe it's easier for some of you, but conceptually understand electronegativity. Do it.
I would agree. I would agree with that. I think we use electronegativity the most. Like we learn the periodic trends in like Gen Chem, but then we actually get to use electronegativity a lot in Orgo. So I think it
Ooh, give me an example. How do we use electronegativity in Orgo? The people want to know.
I'm thinking like, I mean, how many times have I written a partial charge on a carbonyl, bro? All because of the
Ooh,
electronegativity of oxygen.
ooh, you talking money now?
I mean, so I would agree with that. I think electronegativity makes a lot of sense, and I think it makes like electron affinity make sense, and then ionization energy makes more sense when you think about electronegativity. And also, I put it right here, like they trend together, and you can see that like a lot of things, electronegativity is trending towards, like fluoride, and so is ionization energy, and so is electron affinity. Yeah, they all kind of trend that way. The only one that trends differently is atomic radius, and I always think of like atomic radius, like cesium is the biggest or whatever. So, however, however you want to learn it, but we're going to show the definitions here. We're going to tell you how we learned it the best. And then we're going to show you how it's tested. So, should I go into like what each of these specific things are? I mean, I have the,
Nah.
yeah, I don't think
Yeah.
so. I mean, this was
Just
my,
pause it and read the definitions.
yeah, I copy and pasted this from my Anki card. So,
Yeah, I can't explain this that any better than it's actually explained until we start showing it in practice.
yeah, I agree. Um, you want to take it or me?
I'll take it.
Okay.
So this was also a passage associated question. But the actual question stem says, which of the following trends has a negative correlation with hardness? So you got to figure out what the bump hardness is first. And in the passage, it kind of told you what hardness is. So if you look at the end of that giant paragraph, it says we would characterize hard acids and bases as having blank. Okay, so essentially, I'm gonna look at this and say, all right, if you fit in that list, you hard. And so hardness is that list to me. So now my question is, which of these has a negative correlation with the list? All right. So I'm looking for as something in the list goes up, my answer choice goes down, or vice versa. As something in the list goes down, my answer choice goes up. Okay. Number A, letter A says electronegativity. All right, well, look at number 4, high electronegativity. So is that going to be a negative correlation? No, probably not, right? Because as you go up, if you have a higher electronegativity, then you're probably going to still have a positive electronegativity. So that's not a negative correlation. That'd be a positive correlation. B says polarizability. Number 2 says they are not very polarizable. So if you're getting more and more hard ions, that means that your solution is going to get less and less polarizable. So more ions, less polarity. That's a negative correlation. So I like B. I'll say maybe B. C is oxidation state. Kind of the same logic for A. I mean, it literally says high oxidation state, and same for charge density too, right? Like it literally just says high electronegativity, high charge density, high oxidation state. And so just by applying the logic I used for A, you can rule out A, C, and D. Okay, this really didn't even super test periodic table trends. This just tested reading
Yeah.
logic.
Yeah.
But you got to be able to notice this stuff in the passage. That's the hard part of the MCAT. The two hardest things in the MCAT are number one, the hardest thing is figuring out what the question is actually asking you. And then the second hardest thing is just like realizing what the passage is actually telling you, picking up on the clues they give you.
Mm-hmm.
If you can do that and you learn all the high yield sciences, like you gonna smack that test.
Yeah. We talk about, me and John always talk about how strategies are so important. And that's because it's not because you don't need to know high yield content. Like you do need to know content, but it's just easy to know content. Like we throw a bunch of content at you and you learn it. You don't just naturally come across, there's no like guide for the strategies, except of course our strategies guide that we created.
Oh, plug. Shameless plug.
But that's why we say that strategies are so important, because as long as you have the baseline content down and high yield content down, if you can apply it, simplify the question, stem, flow chart your passages, interpret your figures, then you're going to see extreme improvements in your score. But I digress. That was the last high yield topic and the last question.
All right. Thanks for hanging out with us. We will see you soon.
Peace.